Good morning, ladies and gentlemen. Thanks for coming back that early in the morning. So we have after our overview day yesterday, we have a very PHY-oriented day today, so physical layer, coverage issues, and all that. So it's my great pleasure to have Marius here with us, and he's one of those very strongly involved with mimoOn. Actually, he has led their signal processing department for quite some years, so he has a very, very good overview what it means to design the physical layer of a Femto cell, of a Femto device. He's now professor at Darmstadt University and of the robust signal processing group. Very interesting topic, I presume. Very strong physical layer background, a lot of signal processing, MIMO, array processing, statistical signal processing. So I'm looking forward to an interesting talk about the PHY layer design challenges we are facing when coming up with the next generation Femto cells. Thank you.
Thank you, Misha, for this brief introduction. Hello, everybody. Welcome to this morning session. So this morning I want to speak about the LTE and LTE-Advanced PHY layer challenges, and I want to give an overview here, mainly from a MIMO's perspective. So this talk is a collaboration with Willem Mulder from mimoOn. And let me leave a few words about the company mimoOn. So mimoOn was founded in 2006 as a venture capital backed startup company, and mimoOn was from day one focusing on LTE, and they were bringing together these three very interesting technologies, which are MIMO, SDR, software-defined radio, so DSP platforms, and LTE. So currently, mimoOn has approximately, actually, 60 engineers working. So the outline of today's presentation is, I want to first give a brief background on the physical layer of LTE and LTE-Advanced. I will start with the frame structure here, and I will look at the basic system blocks. I will consider here the downlink because due to time limitations, and I will focus in the second part mainly on the different MIMO modes that are implemented in LTE and LTE-Advanced. So from a downlink perspective, I will look at open loop versus closed loop MIMO. I will look at codebook-based precoding and versus non-codebook free beamforming design. And I will also look at how the channel state information feedback is incorporated in LTE. And finally, I will look at the topic of Femto cells. How can we use these MIMO modes in LTE to efficiently limit interference between the Femto cell and the macro cell network? If we look at the evolution of LTE and LTE-Advanced, we see that there's a constant increase of bandwidth and bandwidth efficiency. We see, for example, in LTE, the peak data rates that were targeted and actually achieved are up to 300 megabits per second, whereas in LTE-Advanced, where we operate on 100 megahertz, we can achieve up to 1 gigabit per second. So this is achieved, of course, as the use of multi-antenna transmission techniques. In LTE, we see that we have in the downlink up to 4 spatial streams that are transmitted simultaneously. In the uplink, there's no MIMO specified. But then in LTE-Advanced, which was standardized in spring, the standardization was completed in spring of last year. There we see that we have up to 8 spatial streams in the downlink, and in the uplink we have up to 4 streams. So let me start with the basic, very basic principles used in LTE. So we know that LTE uses orthogonal frequency division multiplexing in the downlink. So OFDM is used in the downlink. So basically the total bandwidth is split into a number of subchannels. So if we have a frequency selective channel, splitting the bandwidth into different sequence of subcarriers allows us to have parallel channels where each parallel channel is basically non-selective in frequency. So this facilitates the channel estimation and also detection. So let us take a look at this frame structure. A frame is organized in, or a radio frame has a duration of 10 milliseconds. This frame is split into basically 20 subframes. Each subframe has a duration of half a millisecond, and or let's say one slot has the duration of half a millisecond, and two slots make one subframe. So let us take a look at one of the slots. Each slot is organized as following. We have for example, if we have a small cell, in this case, we have a slot structure as given here above, where this slot is divided into a sequence of 7 OFDM symbols. So for each OFDM symbol, we have a cyclic prefix appended that is here in blue. So this cyclic prefix is there to prevent inter-symbol interference. And basically, we have here an OFDM symbol. We have 7 OFDM symbols. Each OFDM symbol or let's take a look at the OFDM symbol in frequency domain. So if we take a look at, if we perform a Fourier transformation, then we can characterize this OFDM or this subframe in the time frequency plane, where we have here in the vertical axis, we have the different subcarriers on which our information symbols are modulated. And on this horizontal axis, we have the time axis, which are basically the OFDM symbols. So in this, if we take a look at our LTE system with 20 megahertz, then we have here up to 120 subcarriers. These subcarriers are further divided. They are grouped by 12 subcarriers. 12 subcarriers make one resource block, and also 14 OFDM symbols in time. They form one resource block. So this is a resource block as illustrated here. One resource block is the smallest quantity in LTE that on which scheduling decisions are made. So basically, this is the smallest time frequency resource that can be used or that can be allocated to a particular user. So in this system, we have the subcarriers placed 15 kilohertz apart, and these subcarriers here, these are denoted as resource elements. In order to allow channel estimation in MIMO, in LTE, we have pilot symbols included on particular resource elements, so on particular subcarriers. They are known pilot signals that are transmitted. Now we have to distinguish different system configurations. For example, if we have a single antenna, then we see here to the left the spacing of the pilot reference signals that can be used at the receiver to estimate the channel, both in time domain, but also in frequency domain. So we see that here we have a sparse placement of the pilot signals, and actually there's of course a trade-off in the OFM symbol, how to choose density of the pilot signals. If we choose the density too large, then this of course reduces the spectral efficiency of the system. Where we have pilot signals, of course we can transmit payload data. On the other hand, if we have a frequency selective channel and if we have a time invariant channel, then we need to have a sufficiently large density of pilot signals. So in LTE it was chosen such that the system requirements are satisfied. For example, if we look at a 2.6 gigahertz system, and if we consider that we are moving in train at the speed of 350 kilometers per hour, then we experience a Doppler shift of 340 hertz. And considering now, for example, Clark's channel model, this corresponds to a coherence time of approximately 3 OFDM symbols. So we see basically that with this spacing of the pilots, we can satisfy the requirements of LTE to still be working in a high-speed environment. Similarly, if we look at the spacing in frequency, then if we consider the coherence bandwidth, so the bandwidth over which the channel is approximately constant, then we see that this is supporting delay spreads of the channel of up to 1.7 microseconds. So these are reasonable numbers, and actually if we look now at MIMO transmission, there we have in LTE the following situation, that different antennas use different reference signal structures. Basically in the time frequency domain, these reference structures are orthogonal. So whenever one antenna is transmitting reference signals, the other antenna is muted. And when the other antenna transmits, the first antenna is muted. So this is to allow the user equipment to estimate the channels without interference, the channels of one antenna without the interference of the second antenna. Similarly, this is yeah, it's basically fixed. It depends on the cell. Different cells have the pilots at different positions, but it's fixed generally. Yeah.
Which channel estimator
The channel estimator is not specified in the standard. That's of course the choice of the manufacturer. Yeah. So usually we look at some Wiener filter in time and frequency, but this is of course not a question of the standard. It's a question of the manufacturer.
So you said it's dependent on the cell, so it's kind of a reading speed or like a frequency reading speed? Like every third, if the same pilot is used, like every third cell? Or
It's configured by the operator. Yeah. Depends on the cell ID and so on. So if we have 4 transmit antennas, then we have the scheme is displayed here. We have 4 antennas with these time frequency patterns of the reference signals. Again, we see that we have orthogonal schemes here. When one antenna is transmitting, the others are muted. We also observe that the third and fourth antenna have a pilot spacing that is more sparse in time and frequency. So this is to reduce the overhead from including these pilots here. Of course, as I said, when pilots are transmitted, no data, payload data can be transmitted at that time and frequency. So there's a trade-off, and we see that, and the idea is, if higher order MIMO is used in the system, then we should have some reasonably static environment. Yes? Channels should not be changing that quickly. We are not traveling at 350 kilometers per hour in this case. So this is illustrating the frame time frequency of a complete radio frame. So we see here this 10 subframes, and we see the pilots included here. What else do we see? We see here for each subframe there's in red illustrated the payload data, the control channel, the downlink control channel where scheduling runs for uplink and downlink. Control information is sent to the different users. We see here the synchronization sequences around the DC. This primary and secondary synchronization sequences, they are here and also here. This can be used by the user equipment to synchronize to the radio frame and also to roughly synchronize the carrier offset. And we also see the broadcast channel that is also 36 subcarriers around DC. So we see that basically this is the minimum bandwidth here. The 36 subcarriers around DC is the minimum bandwidth that each LTE cell must have, because every LTE cell should be able to transmit these synchronization sequences and the broadcast channel. Yeah? Yes. Yes. Actually, you must always detect the, I mean, you always need to track the synchronization sequence because you may have some sampling drift. Yeah. So this is always done. You can, if you want, you can. Yeah. I mean, but you need to make sure that you are in your timing. I mean, that you are synchronized to your cell. Also, you need to monitor different other cells. So you're not only monitoring this for your cell, but also for other cells where you have to perform measurements.
And at the same time, can you be decoding data on the other subcarriers?
I mean, you must decode. I mean, you must be able to do this simultaneously. Okay. Yeah. So we see that actually, since we are sampling at 30.7 megahertz, we see that we are actually occupying more than 20 megahertz. So only from if we have in such a system we have 2048 subcarriers, but only the 120 subcarriers around DC are used with are used for data and control. Yeah? So these others are guard bands which are not used. So we are basically oversampling in this system. Let me show you the basic blocks in the downlink data channel, the physical downlink shared channel. So that is the transmitter side. If we have a package arriving from higher layers, so-called MAC PDU, it's arriving. That is a transport block, and this transport block we are appending a cyclic redundancy check, some bits that can be used at the receiver to detect whether the symbol is or the package is received correctly or whether a retransmission needs to be initiated. So this transport block is then segmented into smaller code blocks, and each code block also has a cyclic redundancy check attached, and that sequence of bits is now entering the channel code, which in LTE is rate 1/3 turbo coder. So for each systematic bit, there are 2 parity bits generated. So we are reducing the rate by 1/3, introducing redundancy, but this is entering then the HAG or the rate matching buffer, which is a cyclic buffer where interleaved versions of the systematic and the parity bits are written, and then not all these bits are transmitted. Actually, rate matching is performed, so only a portion of this total buffer is transmitted at each time. And this, of course, depends on the channel conditions. If we have very good channel conditions at the user equipment, which is reported from the user equipment, then only a few bits are selected to be transmitted. And then after, if this transmission was successful, the user equipment will make an acknowledgement. So in this case, this buffer, this hard buffer can be emptied and another transmission can be initiated. If the transmission was not successful, then a not acknowledgement will be received from the user equipment. And from this circular buffer, a different version of bits will be transmitted, which will be at the receiver merged with the initial transmission to hopefully detect now correctly the transmitted package. So at the output of the rate matching buffer, the code blocks are appended again, and we have a scrambling sequence. Basically, we are multiplying with zeros and ones to make the data more spatially more independent. Then this is entering the modulator. In the modulator, we, of course, also depending on the channel conditions, we either use QPSK 16 QAM or in very good channel conditions also 64 QAM, to which we modulate our bits. So then this is one transport block which is arriving. So we have in case that we have just a single stream that we want to transmit, we have only a single code block, transport block. However, if we are using MIMO, we can transmit more than one stream simultaneously. And in this case, we have a parallel, another transport block, which may have a different code rate and also a different modulation scheme arriving here at this level. So these up to two transport blocks can now enter the layer mapper, and in the layer mapper we actually adjust the number of streams that we have for MIMO transmission. So if in case we have, let's say, a 4x4 MIMO system, we can use up to 4 streams that we simultaneously transmit from our antennas. And this is achieved here in the layer mapper, where these 2 code blocks are now further multiplexed into 4 streams, or this is called, these are the streams in LTE are called layers. So we have now 4 layers arriving at the MIMO processor. So in the MIMO processor, we are actually performing a MIMO precoding. I will speak about this in detail later on. After the MIMO precoding, we have the different antennas signals at the outcome. Still, we are, of course, on the symbol level. That means we are in the frequency domain still. So the symbols arriving here are mapped in the frame builder in the time frequency plane. So we put our symbols wherever no reference signal is present, and then we have the total radio frame. We include the broadcast channels, the control channels, and we also the reference signals and the synchronization signals we include in this radio frame. And at the output, we perform basically a transformation back to time domain. So our frequency signal, our OFDM signal, is converted into time domain with the inverse FFT. The cyclic prefix is appended. So this is to ensure that intersymbol interference is omitted. We have pulse shaping, and then this is transmitted from the 4 antennas. So this frame building process is performed 4 times for the 4 antennas. This is then transmitted over the radio channel. At the receiver, I want to skip this. At the receiver side, we perform the opposite processing, and if there's no correct reception, then an acknowledgement command will be reported, and retransmission will be initiated. So let me, please.
Why are there two CRCs?
So these two CRCs are there, so you don't need to wait for a complete transport block to arrive. You can also make decisions whether there's a correct or false reception based on these short code blocks. Yeah? So that allows you to save time, and you can immediately initiate a retransmission. Yeah?
One more question.
Yeah.
For one PRB, can different PRBs have different modulation and coding rates even if they are for the same user?
PRB?
So resource blocks. Can they have different modulation and coding rate even if they are for the same user?
No, this is not.
No?
Not for a, yeah, if they are from the same code word, then yes, but not, I mean, you can have two code words. Each user can have up to two code words, so also two code rates and two modulation schemes. This is the only
So that's the maximum,
restriction.
okay,
Yeah.
for each user.
Yeah. So in LTE we have the following MIMO modes. 1 to 7 are from release 8, that is LTE. In release 9 and 10 is LTE-Advanced. We have further MIMO modes. So let me briefly overview those. So we have single antenna mode, which is of course not a real MIMO mode. That is the transmission mode 1. Transmission mode 2 does not require any feedback of the channel state to the transmitter. This is based on orthogonal frequency division, orthogonal space frequency block coding. Antenna transmission mode 3 is an open loop spatial multiplexing. So open loop means that there's also no feedback from the receiver to the transmitter. Channel state information is not available at the transmitter. And this mode basically consists in a random type of beamforming. So we are transmitting with different beams on different resource blocks. Then we have closed loop spatial multiplexing, where there is some feedback from the receiver to the transmitter, and this feedback basically consists in Codebook-based decoder selections. This is also in mode 4 extended to multi-user MIMO. Up to 2 users can simultaneously transmit. We have a special mode for the case that we have a rank 1 channel, but the real MIMO modes or higher order MIMO modes are facilitated here in mode 7 to 9. In fact, in the mode 7, that is a user-specific beamformer, that is or beamforming mode. In here, the beamformers that can be designed are, or let's say the base station is free to design the beamformers that it wants to take. There are reference signals that are specifically signaled for particular users, which are used to inform the users about the selection of these beamformers. We'll speak about this later on. This concept of user-specific reference signals and non-codebook-based beamformer design was further enhanced in mode 8, where up to 2 code words could simultaneously be transmitted, or 2 layers could be transmitted. And in LTE-Advanced, up to 8 layers can be simultaneously transmitted on the same time and frequency resource. I will show you in detail what that means. So,
who decides which transmission mode you are going to, like the base station or the user?
yeah, the base station is configuring this. Yeah, it's based on channel conditions, but this is purely up to the operator or the manufacturer. Yeah, so I mean, you want to have a highest spectral efficiency as an operator. Yeah, so you.
So change depends on the channel nature.
It depends on, for example, if you have a user which is quickly moving, yeah, in a high-speed train, let's say, then you don't want to serve him with, for example, a closed-loop scheme, because the feedback by the time it arrives at the base station will already be outdated. So this user you would probably serve based on an open-loop scheme, yeah, so without feedback, yeah. On the other hand, if somebody is at home or in the street with a static scenario, so there, I mean, closed-loop schemes make perfect sense because you can have high data rates towards that user. Yeah. So there's, I want to just briefly touch this. There's an open-loop scheme without feedback that is based on space frequency block coding. The famous Alamuti code is used here, and basically we have diversity order of 2 here. Always 2 symbols are transmitted from 2 antennas, where the other antennas are muted. And this orthogonal space frequency block coding scheme is particularly interesting or attractive because it allows symbol by symbol detection. So the detection scheme is very simple in this case. I don't want to further elaborate on this because I want to focus more on the spatial multiplexing techniques here in this talk. So if we look at the textbook, then we know that if we have a MIMO channel, in order to achieve capacity, the optimum transmission scheme would be basically to convert the MIMO channel into a set of parallel channels. So this can be done, this can be done, for example, by a linear transformation at the transmitter and at the receiver, and also proper power allocation to different streams. So, in fact, from textbooks we know that the optimal strategy is to perform a precoding, which is a linear transformation with the right single eigenvectors of the channel covariant of the channel matrix H, and at the receiver we should make a post-processing step, basically a receive beamforming based on the left singular eigenvalues. And then we should, this converts the channel into a set of parallel channels as illustrated here. And this scheme is achieving the maximum throughput that is possible on a MIMO channel if we also allocate the power according to this well-known water filling principle. So in fact we should allocate most of the power to the strongest subchannel and only let's say less power to the weaker subchannels. So this is known from theory, and the question is, how is this implemented in an LTE system? The basic requirement to perform this, of course, that you should know the channel matrix at the transmitter, because only if you know the exact channel matrix at the transmitter, you can figure out which linear transformation you should use, and also which streams, how much power you should allocate to which of the parallel streams. So let us take a look how this is enabled in an LTE system. So this, as I say, requires feedback from the receiver, or it requires channel state information at the transmitter. So let's take a look at such a MIMO system. Let's say we have 4 transmitter antennas, and we are transmitting 2 spatial streams over these 4 antennas, as illustrated here. So as a receiver, we can perform the channel estimation. As I said, the resource, the reference signals are included, so the channel can be estimated for each of the frequency bins. And then this channel at the receiver, we can now decide which kind of pre-coding, which linear transformation should be used at the transmitter. So the receiver has this information about the channel from channel estimation. It can decide which pre-coding matrix should be used, basically which beamformers should be used at the transmitter for each of the streams that are simultaneously transmitted over the channel. And it could also figure out, this receiver can also figure out which rate, so which code rate at which modulation scheme can be supported by each of these streams. So this information is generated at the receiver from channel measurements, and then this is performed as following. Here at the receiver, not at the receiver, the code, or let's say at the receiver, a particular pre-coding matrix that shall be applied is selected from a codebook. So if we have 4 antennas, there are up to 16 different pre-coding matrices that can be selected by the user equipment. The index of this codebook is signaled back to the transmitter along with a so-called CQI value, which basically defines the rate that is selected for transmission. I will show you later how this is performed. There's also a rank indicator that is used here to define the number of streams that are used for the transmission. So in this case, as I've illustrated here, we have a rank of 2. So 2 streams are used for the transmission. So if we take a look at this pre-coding scheme as it is implemented in LTE, we have 2 transport blocks arriving in a 4x4 MIMO system. 2 code blocks with different code rates and different modulation schemes are arriving from the MAC layer. So we have turbo encoding here. Each transport block has a different code rate, so the rate matching buffer is selecting a number of bits according to the targeted code rate. A modulation scheme is used for each of the transport blocks. Then we have the layer mapper, so each code block can be further multiplexed into 2 streams. So in this case, I consider the case that we have actually a full rank channel, which is, we have 4 streams transmitted simultaneously. And then we have here the pre-coding. So these layers, the symbols are multiplied or linearly transformed with this pre-coding matrix W. And W is, as I said, chosen from a code word, from a codebook. So we have up to 16 different matrices that can be selected, and I have indicated here 4 of these matrices, 4 possible matrices. So we see that these are very simple matrices. The other 12 are obtained from this set of matrices by permutation of the columns. So we see that the choice that we have for the precoding matrices in this closed loop scheme is very limited, in fact. So after the precoding, we have the frame mapper, and then we convert the signal back into time domain and transmit it over the air from all of the antennas. So let us, in the following, take a look at how this, as I said, the CQI reports are generated at the user equipment and how the precoding matrix indicator is selected. So how do we select the code, the precoding matrix? So this is, in the user equipment, this is done based on measurements that are carried out. So in fact, at the user equipment, for each stream arriving, or for each possible stream, the SNR and SINR measurement is carried out. So the signal conditions are measured, and then, depending on these measurements of the SINR, we can select, the user equipment selects the code rate and the modulation scheme here on the left side. So the code rate and the modulation scheme is selected for each measured SNR value such that a bit error rate of 10% is achieved. So the target in LTE is basically to have retransmissions in 10% of the times. Yeah, so we should not always have perfect transmission. It's more effective if every once in a while you have a retransmission. So the user equipment is performing SNR measurements, and based on these measurements, the modulation scheme is selected, either QPSK, if the channel conditions are better, then 16 QAM or even 64 QAM is used. And also the code rate is selected as the SNR increases to higher SNR values, then larger code rates are used. And basically the user equipment is now signaling back this index, and this index is indicating the base station, it's telling the base station which is the preferred modulation scheme and the preferred code rate with which a bit error rate of 10% can be achieved. There are also, in this reporting, of course, you have 4 bits that you need here to report these 16 values. There are also some more compressed schemes. If you want to, for example, report, generally you need to report this based on a given bandwidth, but of course, so you need to generate several reports for each particular sub-band, but you sometimes also want to generate such SNR reports based on a larger bandwidth. So to achieve this, you need to have some way to estimate the effective SNR on this bandwidth. So let us take a look at how this SNR can be estimated. So if we consider a 4x4 MIMO system, and let's assume that we have a full rank channel, then the channel matrix containing the different transfer functions between all transmit and all receive antennas, this forms a 4x4 matrix, and let's partition this matrix into these 4 columns, HK1 to HK4, where basically K denotes now the subcarrier that we consider, and then let's take a look at the received signal. At the receiver, we have a signal yk, so that is on subcarrier k, which is equal to the channel matrix h of k multiplied with the transmitted symbol vector. So this is the symbol vector after precoding. So we see that, in fact, this symbol vector after precoding is the symbol vector before precoding multiplied with some particular precoding matrix. So for these signals that we transmit, we can estimate the SINR values. If we also define the energy per bit that is transmitted as gamma hat, then, depending on the MIMO receivers that we have, the SINR, the signal to interference and noise ratio, can be computed from this formula. For example, if we have an MMSE, a simple MMSE estimator. So in these SNR values can be computed now for every subcarrier. So subcarrier index is k. It can be computed for each of the layers. So we recall that we have up to 4 layers in this scheme. So we have the layer index I, but also for each of the possible precoding matrices. We can also compute it for each possible precoding matrix, one of these 16 matrices. So there are different SNR values which we can compute, and of course we are interested in finding precoding matrix which is maximizing this SNR value. But in the end, what we want to report is some average SNR values where we average over all layers, at least 2 layers we want to average, and we also want to average over the different subcarriers. So how can we average this? Of course, it does not make very much sense to average SNR values. This is not giving us a meaningful value. In fact, we have to somehow find a different scheme to average this, to come up with an average or effective SNR value. For example, if we have an uncoded system, it would make sense, for example, to compute, instead of averaging the SNR, we could average the rates. So there the capacity would come into place, and instead of averaging SNR, we would average the logarithm of 1 plus SNR, which is effectively a measure of the achievable rate in this system. So this is one way to compute an effective SNR, so an SNR corresponding to a larger bandwidth. There are, of course, other methods to compute the average SNR in a coded system that can be found in literature. So let me speak about different forms of reports that can be generated from the user equipment. So there are different modes or different ways to report the channel quality in a LTE system. So some are used for open loop. So in open loop, there's no precoding matrix signaled back to the transmitter. There's only the channel strength is signaled back. But there are also closed loop schemes, and in closed loop schemes, along with the modulation and code rate that is supported, we have precoding matrices signaled back. So let me show you some of these reporting modes. A very simple one that is used, for example, for SISO transmission is illustrated here. So let's say we have here the frequency, we have the different subcarriers or the resource blocks here on the vertical axis. Now we have the channel strength that is changing over, or we have a frequency selective channel. Now we perform measurements on this subchannels, and each subchannel has a different strength. So what is reported here is a CQI value, an average CQI value as computed. I showed this on the previous slides. This is reported with 4 bits, and then differential to this average value for each of the subbands, for n subbands, there are also CQI reports generated by how much there's an offset to the average CQI value. So this is allowing now the scheduler of the base station to select the appropriate code rates, the resources on which the user equipment is scheduled, and so on. So there are, yeah?
Sorry. If we have to send a differential for each of the sub bands, then what is the use of average wideband value?
So average, yeah, first of all, it allows you to use less bits for the subband reports, because you see that subband reports are only 2 bits, which indicate the offset to the average. Yeah. So that's the reduction. Yeah. Yeah. Basically, that's the main purpose. Yeah. So there's another scheme for closed-loop spatial multiplexing, as illustrated here. So we have now 2 code words, and for these 2 code words can, of course, be further split into 2 layers. So reports are always per code word, even though it may include 2 layers. And for these 2 layers, also the differential subband reports are generated along with the wideband reports. So these are in total the number of bits that are signaled in the report. But on top of this, there's also a pre-coding matrix selected. So one of these 16 matrices is selected if we have a 4x4 system. So this is another 4 bits in the 4x4 system, plus a rank indicator which tells the base station how many streams are preferred. So there's another reporting mode in LTE that is based on selected, or it's based on a selection of the best subchannels. That is, this selection is performed by the user equipment. So after taking all these measurements of the channel, the user equipment can now create a bitmap of subchannels, and this bitmap is sent to the base station. So basically, the user equipment selects L out of these N subbands and reports, first of all, the location, so with a bitmap that is signaled to the base station, and along with the average CQI value, average channel quality, if all subchannels were used, not only the selected one, and differential quality measure if only the selected subbands are used for transmission. So this allows the base station, it gives the base station some information about the preferred resources on which the user equipment can be scheduled. There's one other very interesting scheme that is given here for closed-loop spatial multiplexing. So here, in fact, we report a wideband quality measure, channel quality measure for both code words, in fact, and then per subband there's also one precoding matrix, one different, possibly different precoding matrix selected by the user equipment. So the user equipment can select for each subband now the preferred precoding matrix. So this gives some more flexibility for selecting optimal precoding matrices, because of course the precoding matrix on a particular frequency may not be optimal for another frequency, as if we have a time selective channel. So this gives you a rough idea about the different reporting schemes that are supported in LTE. So this shows how channel state information can be signaled back to the base station. However, as we see this in terms of spatial processing, these schemes are very limited, because the spatial processing, basically the precoding, is based on codebooks. So the spatial, the capability of reducing interference in the system among the users is very limited. So in the following we will look at different schemes or MIMO schemes in LTE that have been recently introduced, which are based on non-codebook-based downlink beamforming. So this is, of course, very important in the context of femtocells, because in femtocells, for example, let's say we have a base station with multiple antennas, and we also have a macro cell in the vicinity. Then, of course, we want to make sure that the base station of the femtocell is not creating any interference to the users of the macro cell base station. So there we need to have lots of degrees of freedom to design our beamformers freely, to not create interference, to basically separate the streams to the different users in using beamforming, advanced beamforming techniques.
One question.
Yeah.
Before, you said that the CQI have to be reported such that a certain error rate is achieved. How do you do that with those averaging schemes? I mean, how do you measure the error rate?
So this actually...
Or how do you map this SINR to...
Yeah, this is... I mean, the user equipment knows, of course, about... Or let's say the user equipment knows how much signal strength it needs in order to support a particular code rate and a particular modulation scheme. This depends on hardware, how good the hardware is. Yeah, it depends on the algorithms that are implemented. Let's say if you have a MIMO detector based on zero forcing, then you will probably not be able to demodulate 64 QAM signals. If you have a sphere decoder, then maybe you can do it at a particular SNR. So it heavily depends on the implementation and the hardware.
Okay.
So, but this is known by the user equipment, and the user equipment has actually this curve here. Yeah, this curve is known at the user
mapping.
equipment, and it also depends on the code block size. Yeah, let's say if I have a long code block, the error correction will work fine. If I have small code words, probably it won't work fine. Yeah, so I need larger SNR. So this is highly dependent on the implementation. Yeah. So. Yes. Yes.
Can be assigned non-contiguous bands.
Yeah. Similarly, as a reporting, there's also the grants. The grants are given also, can be given with a bitmap. Yeah, so that's possible. So let's continue here. So I was speaking about the femtocell and that we need more degrees of freedom to design freely our beamformers to form, for example, beam patterns as illustrated here, where we have deep nulls towards the direction of the mobile of the users connected to the mobile station, because of course an operator will only allow us to deploy a femtocell if it's not creating too much interference to the macrocell users. I will speak about this a little later towards this presentation, towards the end of the presentation. So let us take a look how this non-codebook-based beamforming is supported in LTE. So it was first introduced in release 8, where non-codebook-based beamforming was only supported for a single stream sent to users. So it was first designed actually to for transmission to cell edge users to steer beams towards those users to increase the cell coverage. So for this, actually, if we design freely our beamformers at the transmitter, we have to have some means to inform the user equipment about the choice of our beamformers. So this is done using user-specific reference signals. So on top of the cell-specific reference signals that each user is receiving to estimate the MIMO channel, we have now some specific signals, specific reference signals, as illustrated here in the time frequency domain. And these signals are in fact transmitted before or included before the pre-coding. So before applying beamforming, the reference signals are included. So in fact, we transmit these reference signals with a selected beamformer. So this is in contrast to the cell-specific reference signals, which are only included on the layers. So this, in essence, means that from a user equipment's perspective, the user equipment sees an equivalent SISO channel. So if it detects the user-specific reference signals, in fact, what the user equipment sees is just a SISO channel, because the reference signals are transmitted with this particular beamformer that is chosen. However, it allows to implicitly estimate the equivalent SISO channel, and that's all it needs to detect the symbols. So in release 9 and 10, this user-specific reference signaling scheme has been further enhanced and evolved. So in release 9, there were up to 2 streams supported by the reference structure. In release 10, we have up to 8 streams that can be simultaneously transmitted. So this is facilitated by these reference signals that are included. So in fact, we have here we see 2 different resource schemes or resource maps that are used. So these resources here to the left in the time frequency domain, and on the right side we see different resources that can be used for these reference signals. On top of this, to further separate these 2 orthogonal resource patterns, we have a space. We use CDMA, so orthogonal sequences are used to further distinguish different antennas. So for each of these, let's say for this resource map, we can use orthogonal sequences to further distinguish between 4 antennas which are using this scheme and 4 antennas which are using this scheme. So this can be separated using this orthogonal code. So this is indicated as here, ++ plus, plus minus plus. These are orthogonal sequences that are used by different antennas. So again, in this case, the antennas are not separated only due to the orthogonal time frequency resources that are used for the pilots, but also the symbols that are modulated on these resources are chosen as orthogonal. So in this scheme, we can have up to 8 different reference signals that we can distinguish, and so at the user equipment we can estimate all 8 channels to the 8 transmit antenna. So we can measure in fact the entire 8x8 MIMO channel in this case. So on top of this, there's also a feedback mechanism implemented in LTE. So we have so-called, so the first, on the previous slide, these reference signals were denoted as demodulation reference signals because they are used for demodulation. On the next slide, we see reference signals that are used for carrying out channel measurements. So even if a user equipment is not scheduled on an 8x8 transmission mode, these reference signals can be used to estimate the channel conditions and to prepare a feedback to the transmitter. So the feedback to the transmitter is also facilitated in LTE-Advanced, and this feedback is based also on a codebook scheme. So similar to the pre-coding matrix, now the user equipment is selecting a set of matrices from a codebook, and these matrices are fed back to the base station. So basically these matrices indicate the channel that is measured, this 8x8 MIMO channel that was measured. So with this we have now the tools basically to design efficient beamforming techniques to separate or to reduce multi-user interference in the network. So let us consider, for example, now a femtocell as illustrated here. We have 2 apartments below here, first apartment, second apartment, and we also have a base station, a macrocell base station in the vicinity. Each of the apartments is equipped with a femtocell base station. We have a femtocell user connected to one femtocell, a femtocell user connected to the other femtocell. We have a macrocell user that is inside the apartment connected to the macrocell here. And now, of course, we encounter different interference scenarios here. This was also identified by the Femto Forum. Actually, Femto Forum, you may know, is a consortium. It's formed from, or it's a consortium of hardware manufacturers active in femtocells. They were pushing forward standardization required for femtocells. So they have identified important interference scenarios here that are illustrated in this table. So, for example, we have the interference. Let's say we have a femtocell user that is transmitting to its base station in the uplink. Then, of course, it's also at the same time creating interference to the base station of the macrocell. Or we have a femtocell that is transmitting in the downlink to its femtocell user, and while it's transmitting, it's creating interference to the macrocell user, which may now, due to interference, not be able to receive data from its downlink transmission from the macro cell. At the same time as we transmit to the femtocell, we also may interfere with a femtocell user that is connected to another femtocell. So we see that here there are many interference scenarios that occur in this setup. So we have to somehow be able to cope with these interference scenarios, and we believe that spatial processing can help here a lot to reduce this interference. So if we have 8 antennas at our femtocell base station, and if we perform non-codebook-based beamforming, then we can form beams towards the desired users without creating much interference to the remaining users, to the users of the macro cell. So let us take a look at a conventional downlink. So let's, in the following we want to see how we can design these beamformers to have spatially selective transmissions. So I want to consider now a downlink, for example, in a femtocell. Let's say I have a femtocell equipped with several antennas, and I want to serve my femtocell users first. So for each user, I can freely design a beamformer. So this beamformer I would, of course, design. So basically, I take the stream for the users, and I now adjust the different complex beamforming weights of the antennas to create a beam pattern that is indicating the signal strength towards a particular direction, spatial direction. So we see here that we design this beamformer such that the signal strength at the user that we want to serve is large or maximized, and the signal strength towards those directions of the other users that are connected to the femtocell should be much smaller. So we should have nulls towards the remaining users. So we do this for every user, for example here, and then for each user we have a beam pattern, and these beam patterns should be as orthogonal to each other as possible. So this is the idea of multi-user downlink beamforming, and let us take a look at this beamforming design that we can choose here. So let us consider the case that we have k single antenna femtocell users. So I will use the notation of cognitive radio here. Let's say in cognitive radio we have a reuse of the spectrum. So we have a licensed user which is a primary user. In our context, this is of course the macro cell because it's a privileged user. The operator will be keen on protecting its spectrum and limiting the interference. So the macro cell is the primary user, and the secondary network is the femtocell network. So we have k single antenna receivers here in this setup of the femtocell. The femtocell is equipped with NT transmit antennas. Now we are transmitting the symbols S1 to Sk. I consider a single carrier system here for simplicity. Yeah? And what we want to do is we want to design the beamformers, so the weights, the vector of the weights applied to each of the antennas for each of the streams that we have. So these are the beamformers U1 to UK, and also the powers that we allocate to each of the beamformers. So the transmitted signal from all antennas is a superposition of contributions for all of the users. So the signals for all of the users multiplied with their particular beamformers and with the power allocated to them. So this sum is what we transmit to the different users. At the receiver of the case femtocell user, we will now see the following. We will have the transmitted signal multiplied with the respective channel vector. So this channel vector is denoted by H1 to HK. So it basically contains the different channel weights, the complex channel weights from the receiver of the femtocell user to the different transmit antennas. So we assume that this channel vector is known at the transmitter, is it from feedback, as illustrated before. So there's feedback between the receiver and the transmitter, or it could also be acquired from the uplink transmissions. So if we have a TDD system, time division duplexing system, so uplink and downlink are performed on the same frequency resource, then these channels can be estimated from the uplink transmission at the base station. So in the following, we will assume that we either know exactly the channels of the users, or we only know the statistics of these channels. So in the case, we could either know the instantaneous channels, or we could know the covariance matrices, the channel covariance matrix of the particular users, denoted by RK for the case user. So in this case, in order to design the optimal beamformers, we could use a quality of service design. So actually we could try to minimize the total transmitted power in the network while guaranteeing a minimum quality of service in terms of minimum SINR at each of the user terminals connected to the femtocell. So this is the SNR can actually be computed using our beamformers from this as this quotient, and we want to guarantee that this SNR is larger than a particular threshold gamma. So in this case, we can have successful transmissions. So this problem is an optimization problem as we formulated it here, and we want to design the beamformers and the power allocation. So this problem has been solved previously from, a number of solutions are found in literature based on convex optimization. From Bochum and Schubert, there are some works, Winston and Otterstan, famous works in which in fact the beamformers are designed. So this problem is converted into another problem which is easier to solve. In fact, instead of solving the downlink problem, we could also solve, it was shown in this work that we could also solve the uplink problem instead. So we could, instead of designing the transmit beamformers, we could equally design the receive beamformers, and they would also be the solution of this optimization problem. So the receive beamformers, designing the receive beamformers is a much easier problem, because in the receive beamformer problem, the constraints are in some sense decoupled. So each constraint that we have here for each of the users in the uplink only depends on a particular beamformer and not on all beamformers. So that is a much simpler design, and efficient solution can be obtained for this problem. However, in the context of femtocells, our problem is even more complicated. We don't only want to limit the interference among users, we also want to limit the interference to users of the macrocell network. So in this case, we have the similar optimization problem. So again, we want to minimize the total transmitted power, subject to quality of service constraints, minimum SNRs for all femtocell users, But on top of this, we have additional constraints. We also have interference constraints to these macrocell users. So the interference that is created at the macrocell users should also be below some interference threshold. Interference, this is sometimes denoted as the interference temperature that is allowed. So we should basically be below the noise floor here. So this problem, or there's a major problem in this formulation, because on top of the channel conditions, on top of the channel information for our femtocell networks, we should also know the channel covariance matrices of the macrocell. And this is, of course, a challenging task to acquire this information. This could, for example, also be achieved from using channel reciprocity if we have a TDD system. But of course, it's much more difficult than acquiring the channel conditions for the femtocell users, because there will not be any feedback from the macrocell users. So we can expect that the channel state information that we have in this case is erroneous in general. So we need a different design in this case. I mean, this problem has also been solved using convex optimization theory. So, however, we are interested in a robust scheme. So we are interested in a beamforming scheme that is that can be used also in the case that our channel state information and our channel knowledge at the transmitter is erroneous in nature. So towards this end, let us. We have considered the robust beamforming scheme where we have, for example, CQI mismatch due to estimation errors, quantization errors, or even delay. So there's a work by my colleague Imran Waid that was published in 2011, where we consider the case of estimated channel covariance matrices denoted by R hat 1 to R hat K plus L for the femtocell and macrocell users. And these are estimated channel covariance matrices which have, of course, a particular mismatch. And this mismatch is modeled by these matrices delta 1 to delta K plus L. So the beamforming problem that we consider now is a robust beamforming approach where we consider the worst case beamformer design in a sense that we still want to minimize the total transmitted power, but instead of having here the true channel covariance matrices, the exact channel covariance matrix, we have the estimated covariance matrices plus some mismatch matrices. And now we want to design the beamformers which solve the optimization problem not only for the estimated ones, estimated covariance matrices, but for all possible mismatches that may occur, for all possible error matrices that can occur, but we, of course, need to limit the errors, and we limit the errors by considering only those mismatches which correspond to a norm with, or let's say, for all mismatch matrices within some ellipsoid. So this gives us a robustness to the beamformer design. And this we do for the quality of service constraints of the femtocell users, but also for the interference constraints for the primary users. So in essence, in this particular case, we have infinitely many constraints. So we minimize the total transmitted power with infinitely many constraints. So for all possible mismatch matrices, we want to have beamformers that satisfy the constraints. So in this case, we can also look at the worst errors that may occur. So we take the minimum of the SNR. So we look at the mismatch matrix which is minimizing this SNR expression, or we look at the worst case mismatch matrix which is maximizing the interference. And for this, we want to guarantee that the constraints are still satisfied. So interestingly, we could convert this problem of the infinitely many constraints into an equivalent problem which in fact has finite number of constraints, and I don't want to go into all the details, but it has a very interesting structure, this optimization problem. It contains two terms which can be identified as penalties for the robustness. So if we compare this scheme to the non-robust scheme, then we see that we have two additional terms which can be basically interpreted as a penalty. So due to this penalty, we have an increased transmitted power in this robust approach. If we analyze further this problem, we see that there's all constraints are basically convex, so this optimization problem can be easily solved with, convex problems can be easily solved with interior point software. However, there's one non-convex constraint, which is a rank 1 constraint here for this matrix WK. And the idea that we use here is the semi-definite relaxation. We simply remove this non-convex constraint, and then we solve the resulting convex optimization problem. And from this solution, if we get a rank 1 solution, we know that this solution is optimal. So we can take the beamformers from this solution. If this solution is not a rank 1 solution, then we need to perform further steps to find an approximate solution that is based on, for example, well-known randomization techniques. Yeah. So with this, I want to illustrate you some simulation results for this beamforming design. So we consider a setup of 4 femtocell users, 3 macrocell users. We have a femtocell base station with 6 transmit antennas. So remarkable here is that the number of transmit antennas is actually smaller than the number of users, total users in the system. So we consider that we have secondary users at some geographical positions with some local scattering around the users, and we have set targets for the quality of service from -9 dB to 0 dB. Noise variance is chosen as 1, and now we have channel mismatch generated within an ellipsoid of diameter alpha equal to 0.25, and simulation results were averaged over 500 Monte Carlo runs. So let us take a look at, let us compare our robust design, which is the green curve, with the non-robust approach. So for different SNR targets, as displayed here, then we displace actually the percentage of feasible simulations or feasible beamformers that we have computed. For our case, we see that as long as the targets, the SNR, the minimum quality of service requirements are not exceeding a particular value, our beamformer design can always, even with mismatch, achieve 100% feasibility. However, if we would use a non-robust design, due to the mismatch, we may, in some cases, end up with an unfeasible beamformer. So this would mean that quality of service requirements in this non-robust design would be violated because of the channel mismatch. This, however, comes at a price that we need to pay, as I said, we have this additional penalty terms for the robustness. So feasibility, problem robustness comes at the price of increased transmitted power. If we look at the non-robust approach, where the total transmitted power versus a SNR requirement has such a shape, in our design we have an increased transmitted power. But compared to competing design, we are using less transmitted power in our design. So finally, let us take a look at the histogram of the constraint qualifications, or let's say the histogram of the normalized constraints. So normalized means in this setup, if we've here plotted the probability for different channel realizations and mismatch realizations. So a value of 1 in this context means that the constraint of the run is exactly satisfied. A value larger than 1 means that the constraint is over-satisfied. A value below 1 means that constraint is violated. So we see here for the non-robust design that sometimes the constraints are satisfied in this area, but also sometimes the constraints are violated. This is due to the lack of robustness and due to the channel mismatch. In our approach, we see that always all constraints are in fact satisfied. So with this, I want to conclude my presentation. The message I wanted to convey in this talk is that spatial processing for interference control is enabled in LTE, and in fact, as we look at the evolution of LTE from release 8 to release 10, we see that from primarily spatial processing techniques which are based on interference randomization by choosing random beamformers, we are now evolving to more advanced spatial processing techniques where we actually form dedicated beams for the different users to actually control the interference among the users. So this is enabled by dedicated demodulation and CSI reference signals which support the design of non-codebook-based beamformers in LTE-Advanced. So I'd like to thank you for your attention, and the floor is open for questions. Thank you.
Okay. First was one half question actually. Okay. A simple question is in this kind of beamforming, non-codebook beamforming, assume that you don't need angle of arrival and angle of departure. Just channel state information is enough.
Yeah.
Do you
want a full answer or half?
Full answer.
So no, the channel state information basically, it can be of different kind. Generally, what you want is you want to have the real channel, the complex channel coefficients of each channel. This may also include, of course, multipath propagation. So if you refer to this the direction of departure, direction of arrival, you are considering the direct path, I suppose. Yeah? So this only works in the case where you have strong line of sight component. Yeah?
So my second question was related to this. Initially, this non-codebook beamforming was suggested for cell edge users, as you mentioned in your slide, and it was supposedly more successful there because of the long distance. Yeah. And having a long distance means you will have sufficient angular separation most of the time. But in Femto cell scenario, having enough angular separation between the primary and secondary user is a kind of far-fetched scenario. And there must be a hardware limitation in terms of beam separation, means angular separation between the null and the kind of bore side of a beam. So based on these 4 antennas, or say even 8 antennas, based on your simulation, how much is the minimum beam which you can get, or angular separation you can get?
Yeah, that is, for example, it is, of course, in our setup we used, for example, 6 transmit antennas, and we have considered local scattering around the receivers, and that is the separation that we have simulated. Yeah, of course, it's as you have more antennas, this gives you more design freedom to design narrow main beams, and deep nulls. Yeah. So generally, of course, as you say, it's correct that if you have more antennas, this can help you to. Yeah.
I want to know the minimum beam width that can be achieved with the real LTE 8 antenna, means MIMO.
Yeah.
Do you have any idea?
No, I don't know the numbers. It depends on the equipment, I would say. Yeah. On the separation also of the.
Based on the typical Femto cell.
Yeah. It depends on also the separation of the antennas.
In
Yeah.
micro cell we had large separation, so we could achieve very narrow beam width. But in Femto we don't have the freedom to have large kind of separation.
Oh, but you can still have half wavelengths. I think that's not a problem. Yeah.
For achieving a narrow beam width,
You need large apertures. Yeah. Yeah.
If you have a wide, you are able to determine the user and primary user location, and you are able to point the nulls and bore side correctly. But if your bore side is wide enough, it's not narrow enough, so you won't be able to separate the interferer. I want to know the hardware limitation, particularly in Femto cells, because of its small size.
Yeah.
And 8 antennas and based on frequency band. So I thought maybe as a hardware manufacturer you could tell me.
No, I'm not we are not hardware, we are software manufacturers. Yeah.
Okay, that's fine. Yeah. Okay, I'll ask a question.
Give on to Zumi. Thanks for your talk.
Thank you.
I just have a question about antenna ports 7 to 10.
Yeah.
Do they have a larger density than the other antenna ports, for example, 0 to 3?
No, it's actually less. They are less dense.
They're less dense.
Yeah. Also, because if we look here, they use the same resources here. Yeah. The same resources for different sequences. So actually you need to assume that the channel is approximately constant over the entire resource block. Yeah, because it should not change over this 14 OVDM symbols. So that's quite a requirement. So for 1 millisecond, the channel should be approximately constant. But the idea behind this is that if you use higher order MIMO, then you would only do this if you have favorable channel conditions. Yeah? So if you are moving in a high-speed train, nobody expects that you can achieve, let's say, 1 gigabit per second download. Yeah.
Okay, and I just have another short question. This might be a bit silly, but ports 0 to 3 and ports 7 to 10. So what happened to ports 4 to 6?
These are it's a silly question. It's a good question. So there are different. So it's a good question. I think these are used for.
I think there's positioning.
Media broadcast services, and I think positioning. Yeah, right.
Okay, thanks.
Is the solution for the optimization problems based on water filling algorithms?
No. They are based on convex optimization, or based on relaxation. We remove the non-convex constraint, and so finally we obtain a convex optimization problem after removing the non-convex constraint, and this can be solved with interior point methods. There are also some iterative algorithms that can be designed here, where we can again use uplink downlink duality. So instead of designing the downlink beamformers, we can design uplink beamformers, and there's a fixed point iteration algorithm that can be used, which converges in a reasonable time. But it's not based on the water filling principle.
Okay.
All right, so I think we're almost closing. Apart from the people who are here, actually, we have some 20 people following live streaming. So I got some few questions. Some have been answered, but one question was there on the use. It related to one of the questions you asked. How can we place eight antennas into a Femto cell? You kind of answered that. So the follow-up question, or another question related to that, was on the potential use of distributed MIMO, so comp type of scheme in Femto cells, whether that makes sense.
Yeah. No, this can be very naturally incorporated in our beamforming approach, and actually we have some work on this.
Okay.
Yeah,
so this is coming then.
For comp, yeah, there's some work. We have a paper in ICAS where we actually try to select. Of course, there's also a large overhead associated with comp transmission. If you have multiple connections to multiple base stations, there's an overhead for channel estimation and also routing the data.
Right.
So you should only do this if you have a clear benefit. So we there propose an integer programming approach where we actually try to optimize which connections to which base stations we should have. Yes?
Okay. Very good. Okay, thank you very much, Marius.
Thank you.
Few logistical items. So coffee break now. There we resume at 11 o'clock, I presume. I'm today a little bit loosely available, so if some people will be jumping in and out. If you have questions, try to catch somebody from CTTC if I'm not around. Furthermore, I have printed the certificates. Everybody who asked me, except one year, I didn't do that. If anybody else needs it, please email me. If you have not received my email from last night, either directly or via the person who registered you, just drop me directly an email. Okay? So coffee is all yours. Thank you.
Die Slides?
Ja, genau.
Hast du runtergefahren, deine Maschine?
Nee, das